4.6 is Introduction to Titration. So our outcome is I can identify the equivalence point in a titration based on the amounts of the titrant and the analyte. So volumetric analysis is a technique that can be used to determine the amount of a substance by completing a titration. So this involves reacting a known volume of a solution whose concentration is known, we call that the titrant, with a known volume of another solution whose concentration is unknown, that's the analyte. The point where enough titrant has been added to completely react with the analyte is called the equivalence point. This point is often marked with an indicator, which is a substance that changes color at or near the equivalence point. The place where the color really changes is called the end point, and your goal is to choose an indicator such that the end point, where the indicator changes color, is the same as the equivalence point, which is when the moles of titrant is equal to moles of analyte. So in order to perform a titration and do it accurately and quantitatively, we have to do a lot of prep work. But when this prep work is done, titrations are very accurate ways to determine the concentration of something that's in solution. So in order to clean analytical glassware, the main three pieces that we use are a burette, a pipette, and a conical flask, which is also called an Erlenmeyer flask. The burette is a long skinny tube with very fine graduations on it, so we can measure the volume pretty precisely. And the pipette is a piece of glassware that only measures one volume. So it measures that volume very accurately. We use that to measure out the amount of analyte that we're going to react. And the conical flask or Erlenmeyer flask, that shape allows you to swirl the solution inside without risk of it flying out the top of, say, a beaker or something like that. So how do you know that a piece of glassware is properly cleaned? We call this volumetrically cleaned. So this is whenever there's no little droplets stuck to the inner surface of the glass. So the water will just run off in like a smooth sheet and won't leave any droplets behind. So the glassware was rinsed with cleaning solution, then rinsed several times with tap water, then rinsed several times with distilled water. So we want to make sure all of that soap has washed away. So the tap water is used to remove the soap, and then another rinse with distilled water removes the tap water. This is also a practical consideration. Tap water is readily available in a chemistry lab, whereas distilled water has to either be made or purchased by the lab. So you don't want to go wasting your distilled water unnecessarily because it takes time to make more distilled water. The next video in this series is how to use a pipette. So the pipette is going to be rinsed with the solution that it will contain before we fill it, because if there's any distilled water left, say from cleaning, it would dilute the concentration of the solution being measured. So to measure an exact volume using a pipette, you attach the pipette to the pipette pump and you're going to rinse it with the solution it will contain. You want to fill it a little bit above the zero line and then dump in the rinse into a waste beaker and repeat. So you want to be careful whenever you go to draw up your solution. You want to place the pipette tip well under the surface, but not touching the bottom of the beaker, because either of those could cause us to get air bubbles in our pipette, and that dead volume is going to cause us to measure inaccurately. So once you've pulled up the volume of solution that you're going to need, you're going to pull it above the zero mark again, and then adjust using the wheel down to the exact desired volume. Then you'll pick up your pipette, move it over to your reaction flask, place the tip of the pipette into the reaction flask, and release the solution using the lever. So if any solution remains in the pipette, like in the tip, don't force it out. The glassware has been calibrated to account for that little drop. The next question is how to prepare a burette for a titration. So we had to do all that prep with setting up my analyte. I also got to prepare my burette for the titration. So just like with the pipette, we're going to rinse it with the solution that it will contain. Again, because if there's any liquids inside, like from cleaning, that would dilute the solution. So I want to fill the burette at first above the 0 mark. We want to make sure there's enough solution to fill the tip of the pipette. We can adjust to 0.00 milliliters later. So to remove air bubbles, again, if we have dead volume in the burette, that is going to impact the accuracy of our results. So to remove air bubbles, you can turn the tap on and off quickly. You can sort of tap the side of the burette while filling. That's my preferred method. Or you can gently shake the pipette up and down. Please don't ever do that in my classroom. But yeah, some tapping or, just turning the tap on and off, that will help. So to read the volume in a burette, usually burettes have an inverted scale, meaning that 0 is at the top and it goes down to whatever volume. But different instruments might have might have it in reverse. But a meniscus is the curve that is formed by water as it clings to the inner surface of the burette. So this is actually due to intermolecular forces between the glass and water molecules. So glass contains silica, and we know that silica is a very polar compound. So this is also called capillary action if you've taken biology. So whenever we read a burette, we always read the bottom of the meniscus. We want to read it at eye level. So when we measure these solutions here, it's the numbers that we know plus one place smaller. So the numbers that we know are the ones that we can count on the burette. So in my first burette, I've got 12, and then 12.1 is my next mark, 12.2, 12.3. So I know the first decimal, which means I should guess the second. So it looks to me like the meniscus is kind of falling in between the 0.7 and 0.8. So with correct precision, 0.75 milliliters. The next one also goes by 0.1. It goes 6, 6.1, 6.2, 6.3, which means that we have to guess the second decimal place. So looks like it's halfway in between, so I said 6.55. The next one here, it goes by ones. It goes 20, 21, 22, 23. So we know the ones place, and we need to guess one place smaller. So it looks to me like it's just under 29, so I'm going to say 28.9. The next one, again, goes by 0.1. It goes 22, 22.1, 22.2. So we know the first decimal, which means we guess the second. So it looks to me like it's right on that 7 line. So I'm going to put 70. And you have to have that 0 there, because if you just put 22.7, then it would look like what we saw in this case, where we had a less precise measurement tool. So to perform a titration, the purpose is to use a solution of known concentration to find the unknown concentration of a different solution. So the titrant is the solution that you know the concentration of. It goes in the burette. So I always remember titrant is in the tube. We are going to find the concentration of the analyte, and we're going to put that into the conical flask. Often whenever you're doing a titration, you first do a rough titration. So this allows you to determine the approximate equivalence point relatively quickly, so that you're not sitting there drop by drop adding your titrant until you reach the endpoint, because that could take very long. So this allows us to get an estimate of where it is and prevents us from missing it when we're doing a real trial. You can use a wash bottle to remove any hanging drops on the pipette. I'm sorry, on the burette. Or you can use it to rinse down the sides of the flask to ensure all the analyte is present in the reaction solution. So when performing a titration, you want to add the titrant through a burette to a known volume of the analyte until the reaction is complete. So the glassware should be prepared to analytical standards. It should be volumetrically clean. There are many ways to know when the reaction is complete, when the equivalence point has occurred, such as using an indicator or a pH probe. So in a titration, we are using a known amount of one substance to find the unknown amount of another substance. So at the equivalence point, the moles of titrant is equal to the moles of analyte. It's a stoichiometric mixture. This means that if we know the molarity and volume of the titrant and the volume of the analyte, we can get moles of analyte and then the molarity of the analyte. What's the difference between the equivalence point and endpoint? So the endpoint is when the indicator changes color. The equivalence point is when the moles of analyte equal the moles of titrant. So you want to carefully choose the indicator so that the endpoint and the equivalence point occur in the same place at the same volume.